So in this lecture, we're going to talk about dynamic arrays and amortized analysis. In this video, we're going to talk about dynamic arrays. So the problem with static arrays is, well, they're static. Once you've declared them, they don't change size, and you have to determine that size at compile time. So one solution is what are called dynamically allocated arrays. There, you can actually allocate the array, determining the size of that array at runtime. So that gets allocated from dynamic memory. So that's an advantage. The problem is, what if you don't know the maximum size at the time you're allocating the array? Okay, simple example, you're reading a bunch of numbers, you need to put them in an array, but you don't know how many numbers there'll be. You just know that there'll be some mark at the end that says we're done with the numbers. So how big do you make it? Do you make it 1,000 big? But then what if there are 2,000 elements? Make it 10,000 big? But what if there are 20,000 elements? So a solution to this, there's a saying that says all problems in computer science can be solved by another level of indirection. And that's the idea here. We use a level of indirection. Rather than directly storing a reference to the either static or dynamically allocated array, we're going to store a pointer to our dynamically allocated array. And that allows us then to update that pointer. So if we start adding more and more elements, when we add too many, we can go ahead and allocate a new array, copy over the old elements, get rid of the old array, and then update our pointer to that new array. So these are called dynamic arrays, or sometimes they're called resizable arrays. And this is distinct from dynamically allocated arrays, where we allocate an array, but once it's allocated, it doesn't change size. So a dynamic array is an abstract data type, and basically you want it to look kind of like an array. So it has the following operations at a minimum. It has get operation that takes an index and returns you the element of that index, and a set operation that sets an element at a particular index to a particular value. Both of those operations have to be constant time, because that's kind of what it means to be an array, is that we have random access with constant time to the elements. We can push back, so that adds a new element to the array at the end of the array. We can remove an element, okay, at a particular index, and that'll shuffle down all the succeeding ones. And finally, we can find out how many elements are in the array. How do we implement this? Well, we're going to store array, ARR, which is our dynamically allocated array. We're going to store capacity, which is the size of that dynamically allocated array, okay, how large it is. And then size is the number of elements that we're currently using in the array. Let's look at an example. So let's say our dynamically allocated array has a capacity of 2, but we're not using any elements in it yet, so it's of size 0. And ARR then points to that dynamically allocated array. If we do a pushback of A, that's going to go ahead and put A into the array and update the size. If we now push B, it's going to put B into the array and update the size. Notice now the size is equal to the capacity, which means this dynamically allocated array is full. So if we get asked to do another pushback, we have got to go allocate a new dynamically allocated array. We're going to make that larger, in this case it's of size 4, and then we copy over each of the elements from the old array to the new array. Once we've copied them over, we can go ahead and update our array pointer to point to this new dynamically allocated array, and then dispose of the old array. At this point now, we finally have our new dynamically allocated array that has room to push another element. So we push in C. We push in D, there's room, we put it in, update the size. And now if we try and push another element, again, we have a problem. We're too big. We're going to allocate a new array. In this case, we're going to make it of size 8. We'll talk about how you determine that size somewhat later. And then copy over A, B, C, and D, update the array pointer, deallocate the old array, and now we have room we can push in E. So that's how dynamically allocated, that's how dynamic arrays work. Let's look at some of the implementations of the particular API methods. Get is fairly simple. So we just check and see. We're going to assume for the sake of argument that we are doing 0-based indexing here. Okay? So if we want to get index I, we first check and make sure, is I in a range? That is it non-negative And is it within the range 0 to size -1? That is, if it's less than 0 or it's greater than or equal to size, it's out of range. That'll be an error. If we're in range, then we just return index I from the dynamically allocated array. Set is very similar. Check to make sure our index is in bounds, and then if it is, update index I of the array to val. Pushback is a little more complicated. So let's actually skip the if statement for now and just say, let's say that there is empty space in our dynamic array. In that case, we just set array at size to val and then increment size. If, however, we're full, we're not going to do that yet. If size is equal to capacity, then we go ahead and allocate a new array. We're going to make it twice the capacity. And then we go through a for loop, copying over every one of the elements from the existing array to the new array. We free up the old array and then set array to the new array. At that point then, we've got space, and we go ahead and set the size element and then increment size. Remove is fairly simple. Check that our index is in bounds, and then go ahead through a loop, basically copying over successive elements and then decrementing the size. The size is simple. We'll just return the size. There are common implementations for these dynamic arrays. In C++, the vector class is an example of a dynamic array. And there, notice that it uses C++ operator overloading, so you can use the standard array syntax of left brackets to either read from or write to an element. Java has an array list, Python has the list, and there is no static arrays in Python. All of them are dynamic. What's the runtime? We saw get and set are order 1, as they should be. Pushback is order n, although we're going to see that that's only the worst case. And most of the time, actually, when you call pushback, it's not having to do the expensive operation. That is, the size is not equal to capacity. For now, though, we're going to just say that it's order n, and we'll look at a more detailed analysis when we get into aggregated analysis in our next video. Removing is order n, because we've got to move all those elements. Size is order 1. So in summary, let's see. Unlike static arrays, dynamic arrays are dynamic. That is, they can be resized. Appending a new element to a dynamic array is often constant time, but it can take order n. We're going to look at a more nuanced analysis in the next video. And some space is wasted. In our case, if we're resizing by a factor of 2, at most half the space is wasted. If we were making our new array 3 times as big, then we could waste 2/3 of our space. If we're only making it 1.5 as big, then we would waste less space. It's worth noting dynamic arrays can also be resized smaller. That's possible too. It's worth thinking about, what if we resized our array to a smaller dynamic array as soon as we got under 1/2 utilization? And it turns out we can come up with a sequence of operations where we have that gets to be quite expensive. In the next video, we're going to talk about amortized analysis. And in particular, we're going to look at one method called the aggregate.